So thank you for the introduction. I'm happy to present this joint work with Benoit Combemale from the University of Rennes and Benoit Lelandais and Marie-Pierre Oudot, my colleagues from CEA. So in this talk, I will present SciHook, which is a tool we designed in a specific context, but with an approach that we believe can be generalized to other contexts. So this specific context is NabLab. So NabLab is a DSL for numerical analysis, which is developed at CEA. And with this DSL, you can define so your variables, which are physical quantities that you want to simulate. And so we can see that you can define the data types are more mathematical in their nature. And so we have simple data types, but also vector and matrices. And we can also attach these variables to mesh entities, which are the discretization of the space in your simulation. So it's really a physics simulation-oriented DSL. Once you have defined some variables, you can define jobs, which are computation units, which will iterate over the mesh to update some variables. So in this case, we are solving the heat equation. So we are updating the temperature at each iteration of the simulation. And then NabLab is also data flow oriented. So we can here see the execution graph of all the jobs that is synthesized by the language infrastructure, which means that language users do not have to specify in which order their computation will happen. The language just analyzes the variables that are read and written to, and it generates the actual control flow graph of the application. So this is on the front side of the language, and then on the back end, we generate several applications for several backends. Mainly, so all of them are in C++, and we can generate sequential applications or multi-threaded applications or multi-process application using MPI. Then we also can target a framework, the Arcan framework, which is a framework for HPC code, an open source framework we use at CEA, but it's also used elsewhere. And one problem that arises is that how do we debug the code that is generated? Because here, the language user of NabLab, they wrote code like this, but then they have to debug code, which is complex code, complex generated C++ code, which addresses a lot of system level concerns and not numerical level concerns. So because of this, we started this project a while ago, which was to provide a debugger for NabLab. And what we did not want for this debugger is to expect that the user start GDB to debug their generated C++ code, where they have to deal with pointers, reference threads, and so on. So this is not what we wanted to do. We wanted to be able to debug the numerical scheme as it was written by the users, which manipulates vectors, matrices, and meshing entities as their first-class citizens. But not only that, but we also wanted to provide a debugging approach that is suitable for scientific computing, because simulation codes are particular pieces of software. Since they can iterate for over 1 million times on the same single line of code. And this makes breakpoint and step-by-step interactive debugging quite unsuited for this kind of codes. And one of the strategy which is more often than we would like used, which is called printf debugging, can be quite tedious because you can just print the value of a variable. You want to do statistical analysis over your arrays, your variables, and so on. And so just printing a trace requires a custom-made C++ logging library that handles complex computation, so it's also a tedious task. So before we proposed an approach, we took a step back and looked at the bigger picture of scientific computing and development in scientific computing. And what we noticed is that it happens in quite a polyglot way, where the mainly used languages are Python, C++, and Fortran, where each language has its own kind of niche, Fortran being the niche of legacy code, mostly, C++ being the most used language, and Python being the most used language for after the simulation to post-process, to create visualization, to analyze the results, and so on. And also lately for doing AI stuff. And this leads to de facto polyglot development. But this polyglot development happens in the sequential process, where we run a complete simulation, and then we change the language that is used to use Python instead and analyze the results. So we thought, why not integrate those languages, meaning C++ and Python? We did not look at Fortran, but in the context of a simulation code. And I should even say in the context of a single simulation. So we investigate a language level approach to make these polyglot practices of post-processing, basically, viable for debugging, and by enabling the interoperability between C++ and Python. So what we envision for our approach is to define a language-level behavioral interface, which is dedicated to instrumentation. So we can call it an instrumentation interface. And with this behavioral interface, this instrumentation interface, we identify all the execution events in a language, so all the language constructs that give rise to execution events that allow interoperability with another language on consistent execution states, so states where the state of the memory is legal to access, basically. And this interface also identifies these consistent execution states, so we can expose them to the other language. So with this language level interface, we can, for any program of the language, derive the program level instrumentation interface, which does declare and derives these execution events and corresponding execution states. And finally, we have an instrumentation runtime, which acts as a bridge between the two language runtimes. So we instantiated this approach with SciHook, specifically on NabLab in the first time. And so this here is an overview of how SciHook works and how it instantiates this approach. So here on the left, upper left, we have the specification of the simulation code, which is typically, in our case, written in NabLab. And from this specification, we can generate the complete simulation code. Note that we also have a case, I won't expand on it, where the specification is not complete, it's only architectural, and it only generates the skeleton of the complete application, not the actual behavior, but we are still able to generate the instrumentation interface from there. So, yeah, so since we define our language level instrumentation interface, we are able to derive all the execution events and corresponding execution contexts for each program that we generate. And this instrumentation interface here interacts with the SciHook library to declare the execution events and to emit them during the execution. So then what the user can do is write instrumentation scripts in Python, which they register for the execution. and they will be run. They will be how to say the SciHook library will be able to execute those scripts when the events, the execution events, are raised by the simulation code. And so these, to do this, the library interacts with the CPython interpreter to be able to actually run the scripts. And the user has access to all the scientific computing libraries that they are used to be using for analyzing the results of their simulation. So here is an example, an excerpt of an instrumentation, a generated instrumentation interface for a C++ application generated with NabLab. So the actual application code is here. And so here we can see that we have a loop that will update this un+1 variable on each cell of the domain. And what we will do is that before this loop, so right at the beginning of this job called update u for updating the temperature, we will instantiate a context for this of the application to be exposed to Python, and then we will emit the corresponding event before and after the execution. And so this context is declared, generated as well, extending the SciHook execution context. And it will expose the memory, basically, as NumPy arrays, so that they can be manipulated with the NumPy library. And this is a view on the memory. There is no copy happening, which allows the language user to directly interact with the NumPy library efficiently. And yeah, and here I didn't talk about it, but this is the registering of the events that we are raising here, which happens at the beginning of the simulation. So what can we use SciHook for? So here we are, this is an instrumentation script, which is Python, which imports the SciHook library, and also the instrumentation interface, which is exposed in Python, to be able to register instruments, what we call instruments, which are Python functions that will execute on the raised events. So here, this function will load a reference solution, which is stored as a JSON file, and will compute the difference between the temperature at the current state of the simulation and the reference solution. And we will then compute the max error over the complete domain. And if this error is superior to 10, which is an arbitrary value, we will trigger a Python breakpoint, which will allow us to enter into interactive debugging, to run some more Python commands to try to understand what is going wrong, or to just kill the simulation because it has no meaning anymore. So this is an illustration of how to use SciHook for debugging, but we quickly realized that it's relevant beyond just debugging. So we are basically in this case here. We were envisioning this case mostly, where we debug the simulation code, but then we realized that it can also be applied when we are trying to validate a physics simulation code with regard to experiments, and most importantly, for when language user needs to define a custom model, like custom physics parameter, like rainfalls or the temperature over the boundary of the domain, or such things. Or they also need to pre-process their data and to initialize their simulated domain with some agility. And here, SciHook is also quite useful because you can do this in Python instead of using filling XML files and so on. So here is a quick example of how it can be used. So here we are using SciHook to implement a lightweight simulation workflow where we have a first instrument that will initialize the temperature over the domain. Then we have a second instrument that at each iteration will constrain the temperature over the boundary of the domain to be 0. And then at the end of the simulation, we will display a heat map of the result of the simulation. And something I've not mentioned is that this allows to have results, to visualize the result without doing any I/O operations, which are the things that take up a really big chunk of the execution of a simulation. So it really allows to iterate quickly to calibrate a simulation. And so speaking about that, here is some performance evaluation where we can see we have two baselines. So here we have a baseline without IOs, where we are not writing any data. So basically the simulation is useless, but it's still computing stuff. And here we are writing the data. And so just to be quick, the monitoring case I showed you is here. And so it shows that by only monitoring and not outputting any data, we can still validate some properties and be faster than if we did dump all the data. And the lightweight simulation is really a huge speed up because of not having to do any IOs. So to summarize, we designed SciHook, which is a tool and an approach to debug simulation codes. And we leverage the existing polyglot practices to make them viable for debugging. The tool relies on a language level approach to generate the necessary instrumentation, which exposes execution events where a dynamic instrumentation can happen and exposes a domain-relevant view of the corresponding application state. And we found the approach to be relevant beyond debugging, and that when instrumentation scripts can replace the original IOs of the application, we can obtain great speed up. So for our future works, we envision additional integration, like being able to instrument directly C++ code with source-to-source transformation. So this is a work in progress. We also envision to integrate directly at the LLVM IR level, and maybe propose a Mojo implementation of SciHook if this language takes off. We would also like to be able to JIT compile our Python script, for example, with Numba, which is a rising library in this respect. And here are a few features we could add to the library. So thank you for your attention.
Time for one quick question, please. Okay, so we are looking forward for the closing session. So I have a question. So when I think about source code instrumentation, I always think something was very popular 20 years ago, aspect-oriented programming. Couldn't you use a system that could instrument the code for you that is part of the motivation for that community?
What do you mean? I'm not sure.
So normally when you want to instrument your code,
yeah.
Okay, you can do it by polluting the source code with implementation code,
yeah.
Or you can have define it in a kind of an aspect that is later weaved to your code. Couldn't you use?
So here, since we are generating the code anyway, this is the polluted code is code that is never touched by the users. So it's less polluted in a sense. But this is also the reason why we want to investigate LLVM to instrument directly at the LLVM level, yeah, to have a more clean approach and to integrate with more languages than just C++.
Thank you. So I think we thank the speaker again.